Okay, the previous video I just deleted, and we're gonna pretend that last 20 minutes did not happen because I labeled the video wrong, right? Today is Saturday. The integer ID of this video is 104. And I'm just cleaning up some test code, and I'll kind of catch up on what's going on here. I was just about to write a comment, so at video 104, this is what caught me and made me realize I was looking at that I did this wrong. At video 104, and the time is 0000, and let's say 42, because we want to be cool, right? So this test down here used to work, right here. This test used to pass until we added the CTT logic to check for different extreme corner cases. So yeah, I was a little bit confused when this was failing because I was like, hey, I thought that we already tested this code and I thought it already worked. And yeah, it worked until we started testing other corners, and then it didn't work anymore. So they got to figure out why that is. But keeping a note of why it used to pass might give us little clues as to how to fix it. Now let's go look at the other code we just finished, right? We just finished some code here. So in order to figure out what's going wrong, we were thinking, oh, we'll just write some test code for this function because this function is used internally by the other function I was just looking at. And so I'm like, maybe we should unit test the component helper functions of the function we're testing, just to see, like, just to see if we can figure out what's going wrong easily, right? So it's pretty easy just to write a simple test function, and if the test function finds a problem with the helper function, that's going to be a little bit easier to, like, if you have a small helper utility function, and the problem is in that small helper utility function, it'd be much easier to solve the problem if that's where the mistake is, right? And unfortunately, the mistake is not in this piece of code I'm testing. And let's explain this code really quick. So, paint pixels converted to canvas user view pixels. UTC right here stands for unit test code, right? So UTC here stands for unit test code. P5D 1 OGL stands for PAINT5D OGL, which is subsystem number 1. AAC 2020 stands for Atomic Alice C 2020. 2020 is the year that it was established, right? So the year the code base was established. So we declare all the variables. We have our loop variables, the current test index, the base address of the current test. Then we have our inputs, the tile quadrant, tile exponent, the tile layer, the tile local x, tile local y. The outputs that we're expecting are cov ix and cov iy, but they're going to be abbreviated as ix and iy. That stands for canvas user view x and canvas user view y. So what we're doing, if we look at the diagram, do you want to reload it? Yes. Let's close that. Let's go over here for a second. We have some diagrams. I put some diagrams in the README. So the canvas user view is kind of like what the user sees, but not exactly. It's a normalized view of what can be on screen. And this canvas is always 256 by 256 pebbles. You could think of it as 256 by 256 tiles, or 256 by 256 pixels. You could think of it as pixels, tiles, or pebbles, but if you want to be completely correct in how I'm abstracting this data, this is in terms of pebbles, and pebbles are the smallest possible tile that can be displayed. And so this is what the user sees on the screen. They see this quadrant for the top left tile they're drawing, top right tile they're drawing, bottom right tile they're drawing, and, sorry, no, this is the bottom right, this is the bottom left. I don't know my left and right, sorry. So, when we're over here, we want to be able to translate from this coordinate space to this coordinate space, and this coordinate space here is the underlying data partitions of the texture memory where we're storing all of the tile values. So sometimes we want to go from a, say, tile layer 1 using tile exponent 0 on tile quadrant number 0. We want to go from that coordinate, and we want to get like a global XY location somewhere on this canvas, this texture, and we want to convert it to a location somewhere on this canvas user view. Sometimes we want to take a canvas user view coordinate and turn it back into a global coordinate somewhere on here, and then from taking that into a global coordinate, then convert it into the PAINT5D coordinate, which gives us, you know, a quadrant, a tile exponent, and a tile layer, and then a local X and Y within that sub-allocation. Okay. So the output is in a struct that actually contains these two parameters here. And the reason for that is this code is going to run on in a GLSL shader eventually. And so we can't do anything fancy like output parameters or anything that involves pointers, because GLSL does not use pointers. And that would be pretty bad if your shaders could segfault. So yeah. So anyways, for the test data, we have the number of tests times the number of columns for every single test. So you could say the number of tests multiplied by the stride. Tab UTC stands for table. UTC stands for unit test code. So tab UTC means table of unit test code. And we're going to go through, these are our inputs and these are our outputs, right? So we've labeled them input and output right here. So inputs and then our outputs. All right, so we've lined everything up nicely. And the first clusters of tests are very basic tests, right? They're sanity check tests. And then we get through to some more complicated calculations. So I don't really feel like explaining it, but let me explain it one more time. So the tile exponent is going to determine this output here. This output is the top. Oh, hey. So I'm just doing some tying up some loose ends before I stop streaming. This is just a really short stream just to like tie up loose ends before. I don't do any work on Sundays, and then Mondays is the one day a week that I drink coffee and I like program for like 14 hours. I try to get to 16, but realistically it's usually 14 hours. And so I'm just trying to tie up some loose ends before I don't look at this code for a day. Like, I don't want to have to come back to this code after not looking at it for over 24 hours and be like, oh, this doesn't compile, right? Like, if you leave code in a broken state, you risk losing your code base. I mean, I've put a lot of effort into this, so that probably won't happen, but it's still a good habit to never leave your code in a broken state. So we just want to make sure that it compiles. Some of my tests are still failing, which kind of sucks, because I'd really like to leave it in a state where like all my tests fail and it compiles and it's all nice. But unfortunately, that's not going to be the case. So I just want to look through these tables and explain them a little bit, and then I'm going to be done here. But yeah, it's just... yeah, look, oh, yep, you got those nice emoticons. Actually, they're probably not called emotes, they're just called emotes. Yeah, so, let me see if I can explain this. diagram. I don't know if you've seen this diagram before, or if I've explained it before. But this this diagram here is a schematic diagram of what the user sees in their viewport. But it's not exactly that. This would be exactly what the user sees in their viewport if their viewport were exactly 256 pixels by 256 pixels, and they were zoomed all the way out onto the entire canvas, right? So this is not exactly a diagram of the client area or the screen coordinates. It's kind of like it's one step removed from that. So like you would map, like you could, like, so say you're looking at this data and you're zoomed in, right? Well, if you're zoomed in, then maybe your viewport is like selecting over this area, and your viewport is going to map this area of the diagram to the screen, if that makes sense. So right here is the top left tile of the auto tile set that my artist is going to work on, and then these are the other 4 tiles that make up one auto tile set. So this is the design view. I'm calling this the canvas user view, this diagram here. And sometimes we want to map, to get the fragment shader to work correctly, we want to map a coordinate on here to this actual data layout here, right? So we want to say, okay, for this pixel that's somewhere on the screen, what data is at that pixel, right? So for any given pixel, there are always 8 tiles underneath that pixel, because we have many different tile sizes, right? We got 128 very small tiles, 64 tiles that are half that size, 32 tiles that are half that size, and then 16 tiles half that size, etc., etc. And they're all overlaid over each other. So for any pixel here on this canvas user view, you're going to have 8 tiles that are all stacked on top of each other. But wait, there's more. Not only are you going to have 8 tiles stacked on top of each other, but you also have 3 separate layers. So, for example, this is the first layer of the smallest tiles for this user view here. This right here is the second layer for all of the tiles in this user view here. And then this is the final third layer of all of the smallest tiles that can be set down here, right? So we have to do a lot of work where we take the fragment shader has to go over each pixel and retrieve would be 16, no, it would be 24. It needs to retrieve 24 different tiles. For every single pixel, there are 24 different tiles that are underneath that pixel, right? Because you have 8 tiles of different sizes, and then you have 3 layers, so 3 times 8, 24. So right here, we are checking the math for some of that conversion logic, and this is paint pixels right here to CoveyPix, and CoveyPix just stands for canvas user pixels. So this is taking a coordinate somewhere here, and it's converting it to a coordinate somewhere in here. However, this paint pixel coordinate is not a global coordinate on here. It's not defined by like an XY location. The paint pix coordinate is defined by the tile quadrant, right? So the tile quadrant could be 0, 1, 2, or 3. And then it also is defined by the tile size exponent. So the tile size exponent could be tile size 0, or tile size 1, or tile size 2, etc., etc. It's also defined by what layer we're on, right? So are we on layer 0, are we on layer 1, are we on layer 2, etc. So when you see that the system name that we're working on is called PAINT5D, so in the bottom left-hand corner of my stream, you can see it says PAINT5D. The reason this subsystem is called PAINT5D is because 1, 2, 3, 4, 5, right? So right here, we have 5 dimensions that are used to define where a certain tile is. What quadrant it's in, the exponent, the layer, the local x, and the local y. Now, originally, it was named PAINT5D because of... Originally, I did not have this tile quadrant. Originally, it was going to be this, and then it was the tile value that was the 5th coordinate, right, for 5 dimensions. Good enough to me, it still works out to 5 coordinates, so, yeah. But I guess, technically, you might think of it as 6-dimensional if you want to consider the color of a tile as a 6th dimension. But, whatever, good enough. So right now, this function here just is going to convert from a 5-dimensional coordinate that locates a certain pixel that's storing a tile value on here, and it's going to convert that 5-dimensional coordinate to a 2-dimensional coordinate that figures out what fragment coordinate we're on. But it's not the exact fragment coordinate because this view may be squashed or stretched or zoomed into. So this isn't exactly the fragment coordinates, but it's like one step removed from the fragment coordinates. So I think I pretty much got that done. I was going to explain one of these lookup tables. I guess I should document one of these lookup tables at least before I go. Let's look at the simplest case, right? So when you're writing our test cases, we want to do something dead simple first, right? So most of these things have been zeroed out to keep everything as simple as possible. So let's look at this first test case right here. The tile quadrant is 0, right? So tile quadrant is 0. So this tile quadrant of 0 corresponds directly to here, okay? The tile exponent is 0, tile layer is 0, tile x, tile y, they're all 0. And so we're expecting the output to be 0, 0. So basically, the input for here is what we see in the cyan. Hold on. So right here is the input coordinates, which correspond to over here. And that actually looks ugly as hell, so I'm going to get rid of that color. And the output coordinates are these ix and iy in orange. And the output coordinate should be right here, like right in this corner here, for this first test case. Now, for the second test case, we see the only thing we've switched is the tile quadrant. So it's going to be this upper corner here, because we're looking at this tile quadrant, right? Well, technically, we're looking at this, and then converting it into something within this space here, and it turns out to be this coordinate here. So for the second test, here, we've only changed this to a 2. So we're saying, hey, we have a coordinate somewhere in here, and we want to map it to somewhere in here. And that's pretty easy, because everything, once again, is zeroed out. So it's the top left corner, so it's 0, 128. So 0 on the x and 128 on the y. And then this one right here is the last cell. So it's this cell here, this quadrant here, this tile quadrant 3. It maps to somewhere in here, and it specifically maps to 128, 128, which is the upper left quadrant here. Now, it gets a little hairy when we are using tiles that are bigger, right? So this is the smallest tile, right? So it's pretty easy to do the math. But as we use bigger and bigger tiles, like tile size 7, the math gets a little different. So, for example, it gets a little bit confusing. So let's say that we are over here and we're using tile size exponent 6. So we're almost using the largest tile size. The largest tile size would be 7 and would fill this entire canvas. Let's say we're using one size down. We're using tile size 6. So we could have a tile here, we could have a tile here, we could have a tile here, or we could have a tile here, right? Because they're really big, we can only have 4 of them. And if we are at not 0, 0, but if we're at 1, 1, if we want to, say, convert this coordinate to a coordinate in terms of this data, the way we're going to do that is... Oh, hold on. So maybe I'm doing this completely wrong. Let me think about this. Nope, that makes sense. So when we're taking a coordinate here for a certain tile, we're not actually taking the tile coordinate. So all these coordinates on the canvas user view are in terms of pebbles. So they're in terms of the smallest tile. So 0 to 255. And so when we have a coordinate for this tile, we want to know what the canvas user view coordinate for this is, right? And the canvas user view coordinate for this is not 1, 1, right? Because sure, for this tile size, this is at 1, 1, but for the biggest tile size, this is at, in tile coordinates, it's at 0, 0. But for the biggest tile, it's at tile coordinate 0, 0, but its pebble coordinate is in the upper left at 0, 0. For a smaller quarter-size tile, its tile coordinate on this view is at 1, 1, but its pebble origin, its pebble coordinate, is actually in the upper left-hand corner of the tile at 63, I believe. So let's look at that, yes. So tile size exponent, if we're at 1, 1, oh, 64, my bad. Because 63 would be the last pebble of the tile at coordinate 0, 0. And so the tile at 1, 1 of this tile size would be origined at 64, 64. So the idea is that when you have a very large tile, there's many pebble coordinates that it's over. So we have to reduce all of the different coordinates to one specific coordinate, right? We have to decide on a very specific coordinate to define its location in terms of the canvas user view. But now that I'm thinking of that, now I'm a little confused, because now I'm wondering if that doesn't make quite, if that isn't the quite sensible way to do that. No, actually that makes sense, because if we have this tile location, the only thing we can really do is when we have this tile location, do you want this pebble over here underneath it? Do you want this pebble under here underneath it? Do you want this pebble under here underneath it? Right? There's a whole bunch of smaller cells that are underneath the gigantic tile, right? So when we're trying to convert this tile coordinate into a pebble coordinate, we have to kind of decide on one location, right? And now that makes sense to me if we're going from canvas user view pixels to this location, but is that what we're testing, or are we going in the opposite direction? Hold on. So this is actually going from PAINT to canvas user view pixels. So now I'm not sure if these calculations are right. Well, let me think about that. Yeah, I'm not sure if that's quite correct. Like, I might not be doing this all correctly. I don't know. So, well, let me think. So on this data set here, there is no... Yeah, so there's information loss when we're converting from this coordinate space to this coordinate space, and I think that is the crux of why my tests aren't working, because I don't think I fully understand the problem, honestly. And if this is going from paint pixels to canvas user view pixels, but the table, as I've been conceptualizing this table, I've been thinking of it in the other way around. I'm not sure if that's quite correct. Because because I feel like this should be a lossy conversion. Converting from, if I convert from this coordinate space to this coordinate space and then back again, I believe I lose information, right? Because everything migrates to the upper left corner here. So I may not have so sometimes when you write tests, it kind of helps you understand the problem better and understand what you're actually doing. Because sometimes you have no clue what you're doing, and then you write the tests, and the tests kind of reveal that you don't really know what you're doing. And now I have to think about if this is actually correct or not, or if that's not correct. Well, okay, you know what? So if we're looking at this coordinate here, right, for the largest tile, then the only thing we know about it if we're specifying the largest tile for this cell here, then the only thing we know about that tile is that it's like this huge tile that covers all of this. And we're trying to convert it to one coordinate on this thing here, but technically the coordinate for this tile here actually covers all of these coordinates here, right? So technically the tile lays on all of these coordinates. It doesn't just exist at one place, it exists at all these different coordinates. And so we have to reduce it just down to one coordinate at the top left origin of the tile. So that makes sense as to why I'm doing that, but I see that losing information like that could lead to my renderer not working properly if I don't properly consider the information loss when converting between these coordinate spaces. My renderer logic might not quite work. And the code that I am actually testing out right now, so if we run the code and it fails, it's going to fail. The code I'm testing is a precursor to getting the rendering logic working, because, like I said, I just want to figure out what tiles are underneath a certain pixel, and I don't know yet. Well, I'm trying to, but my tests are failing right now. So it says failed, and the failure is canvas user view pixels to canvas user view bits. So what that means when I'm saying canvas user view pixels to canvas user view bits is I'm saying, okay, we're going to use a pixel coordinate somewhere on here. Technically, it's a pebble coordinate, like if we want to use a lot of times I abstract everything as pixels, even though they might have a better classification. So a canvas user view pixel is actually if we want to be pedantic about my mental conception about what's going on, a canvas user view pixel is actually a pebble coordinate, right? And a pebble coordinate is just the smallest possible tile that can be displayed. So when we're trying to address this canvas user view space, we want to address this space in terms of the smallest possible tile that can be displayed. Because if we have enough addressing space to address a very small granular tile, then we also have enough addressing space to address a gigantic tile, right? Because a gigantic tile that covers the entire screen, or the entire quadrant here, its only possible coordinate is 0, 0, right? And then for smaller tiles, the smaller the tiles get, the more of them you need, so the more numbers you need to address all of them, right? And so we don't want to ever use more bits than is necessary. So the minimum amount of bits that we need to address all of this space would be making the smallest tile our unit. The smallest tile is our addressing unit, or sometimes I say that the smallest tile is the quote-unquote Planck unit, like in science, where they hypothesize that there's this like hypothetical unit of measurement where no measurement can get smaller than that, right? Like if the universe was a if the universe was a giant LCD screen, then a Planck unit would be 1 pixel on that LCD screen, right? You can't divide any deeper down than 1 pixel. So yeah, so these calculations here seem to be failing me, where I'm trying to just sample a pebble coordinate on this canvas user view and get back all of the different tiles that are underneath it. So let me run this one more time, because I lost track of where that is. I want to make a note of what's going on, and for next time. So let's wait here. So we failed this function here, so let's take this and kind of put this in here. So this is where we're failing, and there's a whole bunch of commented out code, but let's just take this gigantic monstrosity. That's the other thing that scares me, is that this test is like, it has a lot of stuff in it. So when things fail, that can be kind of scary, you know? But let's just make some notes about what is going on here before we quit for the day. And like, why are we doing what we're doing, right? So let's make a little documentation for this, like, right here, I guess. Okay. Canvas, user view, pixel, chord. Convert to, actually this is lowercase, canvas user view pixel chord, convert to canvas user view bits. So we want to look at a certain pixel on the canvas user view and figure out what tiles are underneath that pixel. The function returns a 16-bit Bitpacked value of all of the 2-bit tile values for a given layer under the specified canvas user view pixel. If we want to get pedantic, a cuv pix slash canvas pixel is actually a canvas user view pebble, right? A pebble being the So really, this thing called QVPix, technically, it would be more appropriately named to call it QVPeb for Canvas User View Pebble, but we already named it QVPix. I'm just going to think of it as a pixel. So when I'm kind of mentally thinking about the transformation of the data, a lot of times I just abstract everything as a pixel. But, right, so I'm thinking of this as 256 by 256 pixels, but it's not really pixels. The only time this is actually pixels is when the viewport is exactly 256 by 256 pixels, and the zoom settings are zoomed all the way out to see the entire piece of artwork that Josh is working on, right? So this 256 by 256 is not actually pixels, it's actually pebbles, but I just feel like it's easier to think about it in terms of pixels, because the pixels is slightly less abstract than calling it pebbles, right? So when I want to reason about this, when I want to reason about the transformations going on over here, I am going to just think, oh, the viewport is currently 256 by 256 pixels, and it's zoomed to be snapped directly onto this entire data set rather than zoomed in like this, or like zoomed over here or something, right? So we made this big explanation of what's going on, so we should also make a note of the video ID of this, so if we ever see it again, we know what we're talking about. And then we're going to have to explain it one more time for the camera, unfortunately. So 36 minutes and 3 seconds. So explaining for the camera, let's just read this really quick. So for this function, we're testing QVPix converted to QVBits. So Canvas User View Pixels convert to Canvas User Bits. Okay, so Canvas User Pixel Chord convert to Canvas User View Bits. QVPix to QVBits. Let's read the paragraphs. We want to look at a certain pixel on the Canvas User View and figure out what tiles are underneath that pixel. The function QVPix to QVBits returns a 16-bit Bitpacked value of all of the 2-bit tile values for a given layer under the specified Canvas User View pixel. If we want to get pedantic, a QVPix / Canvas User View pixel is actually a Canvas User View pebble. A pebble being the smallest possible tile value, our proverbial graphical Planck unit. However, I tend to abstract everything as pixels, hence the name QVPix, and a name means whatever I decide it means, so to refactor to QVPeb would be a waste of my time. Right? So we've read that little documentation, and to supplement that, this is the Canvas User View we're talking about, and it's 256 by 256 pebbles. Now, a lot of times we can think of these pebbles as pixels, but we can only think of these pebbles as pixels if the GL viewport is exactly 256 by 256, and the camera is zoomed as to be snapped exactly to this data set. And if the camera settings satisfy those criteria, then we can reason about this as if these coordinates were pixels. And that's actually a very helpful way to reason about it, because the way my fragment shader is going to work is it's going to map a screen coordinate to a coordinate on this Canvas User View. Then it's going to say, hey, for this Canvas User View location here, what are all of the tile views underneath here, right? So we have to convert this Canvas User View coordinate to a Bitpacked value that contains all of the tiles that are underneath the pixel that is mapped to this Canvas User View coordinate. And because there are 24 different tiles underneath every single pixel, and because we have 2 bits per tile, well, 24 times 24 is 48. That's more than 32. So we can't pack everything into a 32-bit integer. So what we're going to do is for every single canvas user view coordinate, we're going to do 3 samples. We're going to do a sample for the first layer and get all of the tiles that are underneath that canvas user view coordinate. Then we're going to sample the second layer and get all of the tiles that are underneath that canvas user view coordinate. And then we're going to sample the final third layer and get all of the tiles that are underneath that canvas user view coordinate. And that's how we're going to render this out. In order to make sure that... So once we get this unit test code working, we'll be well on our ways to getting a rudimentary renderer working, right? And the first go of the renderer will not have any camera movement or camera controls into it, right? It'll just be a static view of this entire data set, and we'll probably just render it always at 256 by 256 pixels, so it'll be really small. But we'll render it like that at first, just to make absolutely sure that we can get that working before we try to add camera transformations onto that dataset. So I just wanted to explain that for video number 104. And began explaining. And then, let's say the video ID now is, it's still 104, but the time is 41:40, and we are done explaining, right? So, right, whenever you have those cases where you're looking at code and you're like, what the heck was I thinking? Well, now we have a nice little comment for this test function and what it's testing and what that code needs to do. And so, hopefully, we never have to go back to this video, right? So the first line of defense is having a nice big comment. And then if the comment doesn't make enough sense to us, we can do this, right? And we can see these diagrams here. So I think I'm good there. I think I just want to be done for today, because I still have like 100 push-ups to do today, and before I'm like done doing everything. So I just wanted to kind of get everything squared away to really hone in on exactly what I am up to, so that come Monday, I'm gonna hopefully blast this out of the park, and figure all of this out. But there's still a lot more challenges, and this is pretty crazy because, like, the whole idea that I'm coding right now, I've been working on this for months, and the original prototype that I made to get me interested in this, the original prototype I wrote, it only took me like a few hours. It took me like 2 hours in JavaScript to make like a little prototype. And now we're talking like months and months and hours, and we're on like video 103. And we're still not to the graphical level of that first prototype I wrote in JavaScript in 2 hours. But the thing is that the prototype that I wrote in JavaScript had the correct visuals, but it didn't have the same underlying data structure, and it didn't have like a nice solid foundation to support rendering on the GPU. It was just rendered on like a canvas, right? So, and it didn't have any camera movements, so we need camera movements, we need palettes, we need fancy shaders to render things, we need to be able to save and load data. So there's like a lot of details, right? So it's interesting that a proof of concept can be like so easy to code, because you don't have to worry about all of the little features that need to go into a properly polished engine. And it's like half the time I'm like, I'm all, what WTF, like all the time. I'm like, how the heck can a prototype be so easy to make so quickly? But then when you want to organize your code properly and meticulously and test it all and have a very solid organization for your project, all of a sudden the work becomes many orders of magnitude more, right? Like, let's think about this for a second. If all of my streams are, let's say, average my streams to 4 hours each, right? Let's say because I don't always get 8 hours in. But let's say that, let's just do some math here, and then I'm gonna get out of here. But let's do some math here for a second. So let's say my prototype took me 2 hours, but I'm on the 103rd stream, and a conservative estimate is that each stream is 4 hours, right? So that's okay. So that's 412 hours. So if we take 412 and we divide that by 2 hours, it takes it's taking 206 times longer. And if we think of orders of magnitude, we have a tens place here, so that's 1 order of magnitude. And 2 over here, that's 2 orders of magnitude, right? So this is 1 order of magnitude, 2 orders of magnitude, 3 orders of magnitude. So it seems, I said many orders of magnitude, but now that I've actually crunched the numbers and I see only 412 hours, so at a conservative estimate, conservatively, 412 hours. So 412 hours, 412 divided by 2 equals 206. 206 times longer than my 2-hour prototype. 2 orders of magnitude greater. So orders of magnitude are pretty coarse in the first place. So if you take a more liberal estimate, so let's say liberally we would double that, right? So let's say that all of my streams are actually 8 hours, which is a complete lie, right? We're saying sometimes we have shorter streams, sometimes we have longer streams. We're going to average it out to 4. Now let's say that we actually did, like, 824 hours. And 824 hours divided by 2 is what? What is that? I can't math. Like 412, right? But I don't trust myself. Oh, of course, because we just multiply by 2 and then divide it by 2 again, right? Of course. So 412 is still 2 orders of magnitude. So that's nice to, like, do calculations in terms of orders of magnitude, because it can let you reason with, like, large margins of error like this, right? So, so 206 and 412, there's still 2 orders of magnitude, right? So it seems to me that to go from a prototype to a polished product, at least for my productivity levels and my levels of thoroughness, a final product seems to be taking about 2 orders of magnitude more work than the initial prototype. So, so we'll make a note of this, and we'll just say, at vid IID, the video ID is 0104, and the time is 0 hours, 48 minutes, and let's just do 49 minutes. The date is 2021-01-23. So we're gonna just take this. We're gonna take these little calculations here, and I like to meticulously keep track of everything I do. So I don't like to waste anything. Like, I took the time to calculate that. So what we're gonna do is we're just gonna dump it into our little hashtag documentation file. So in documentation, we got this little hashtag file we use, and then everything else we've been ignoring. And we're just gonna paste it into here. We're just gonna say orders of magnitude from proto to final. That's kind of wordy, but that's a nice section name, so we'll just put this here. And we just have this This is just going to be buried in our documentation somewhere. We're never going to find it ever again. We could also do hashtag orders of magnitude. And if I ever want to find it, it'll be somewhere in there, and it's recorded on video. So yeah, I don't feel too motivated right now, but I just wanted to get some loose ends taken care of. Also, it's 9, which means I need to take drugs anyways. So I'm going to stop the stream. I'm going to get out of here. I don't know if you're still around, but I'm out of here for now. So night. Alright, still here? Awesome. So yeah, I'm gonna get out of here. But yeah, you'll probably see me Monday sometime, because Monday, I'll probably start at 1 p.m. on Monday, judging by how I usually do things. 1 p.m. Monday, I'm gonna drink some coffee and actually be motivated. It's interesting, because, right, since I only drink coffee on Monday, I get super motivated on Monday, and then the rest of the week is just me kind of, like, hating my code, because it's like, I have to, like, clean up. I have to clean up after myself for everything I did Monday and do a whole bunch of tedious stuff. But, right, you can't be super motivated all the time, right? So you have to trudge through stuff, right? So you have to have a strong enough vision to stick to it when it's not fun. For me it's fun maybe like 2 days out of the week, maybe it's actually fun for me. The rest of the time I just hate it. And that's why, like, when you distract me and I want to show you something or whatnot, right, then that actually is good for me, because sometimes this is just tedious. So yeah, I'll see you around. But yeah, I'm really banging my head against a wall with my work right now. Yeah, I totally get it. So yeah, so hopefully not having to work tomorrow, I'll just figure out what needs to be done a little bit better by removing myself from this for a while. But yeah, so I'll see you around. Good seeing you, and good to see that we got these emotes going. So awesome. Later.